Here's a strange thing about mathematical models. You can take one single phenomenon, say a population of rabbits growing in a field, and describe it in a dozen completely different ways. Not because one is right and the rest are wrong, but because each one is a different lens, pointed at the very same world. So, before we build anything, it helps to ask, what kind of model is this, really? And it turns out there's a small family of questions you keep asking over and over. Think of it as a decision tree with a fork at every branch. The first fork. Do your quantities flow, or do they jump? A continuous model lets a variable be anything, position, temperature, time, gliding smoothly through every value in between. A discrete model only allows separate, countable steps. Because, look, a population can be 3 rabbits or 4, but never 3.7. Second fork. Is there luck in the room? A deterministic model has none, same starting conditions, same outcome every single time. Throw a stone at a fixed angle and speed, and it lands on exactly the same spot again and again. But a stochastic model bakes in chance. The outcome isn't one number. It's a spread of probabilities. That's how you capture noise or measurement error, or the scatter in a real population. Third fork, and this one really matters. Is the model linear? If it is, you've hit the jackpot. Linear models obey superposition. The response to 2 causes at once is just the sum of the responses to each one alone. So you can break a hard problem into pieces, solve them separately, and add the answers back up. Nonlinear models don't play so nicely. You can't just add pieces up, superposition breaks. They're harder, sometimes much harder, to solve. But that's the price for real power. Nonlinearity is what lets a model bend, saturate, snap, and even tip over into full-blown chaos. Things a straight line could never dream of. Fourth fork. Does time show up? A static model doesn't use time at all. It captures a system frozen, at rest, in balance. A dynamic model tracks how the system changes as time rolls forward. And those are usually written as differential equations in the smooth case or difference equations when the steps are discrete. And the last fork. Where did the model come from? A deductive model comes down from theory. You start with a known law like Newton's, and you derive the specific case from it. An inductive model climbs up the other way, out of data. You gather piles of measurements, spot a pattern hiding inside them, and fit a curve that hugs the points, even when no known law stands behind it. Now, here's the part people miss. These forks aren't rival camps. They're not either-or. A single, real model usually picks one leaf from every branch at once. It might be continuous and deterministic and nonlinear and dynamic and deductive all at the same time. Which raises the real question. In all of this, where does the mathematician actually stand? Because, and this surprises people, the mathematician usually isn't the expert on the rabbits, or the physics, or the economy. And that's completely fine. The mathematician's job was never to be a biologist. The deep knowledge about the phenomenon itself comes from the specialists, the physicist, the biologist, the economist. They hand over what the thing does. The mathematician takes that raw description and builds the correct mathematical picture of it. So think of the mathematician as a bridge. On one side, raw, messy reality described by every other science. On the other, a reliable, checkable statement, written in the language of mathematics. The job is to shape the model, to design a way to solve it by hand or by number crunching, and to lay the groundwork for the next model that comes after it. So the next time you see a model, don't just ask if it's right. Ask what kind it is, where it sits on each of those forks. And remember the quiet figure standing on the bridge, turning the world into something math can finally hold. Same world. Just, at last, a language we can reason in.